This time in the Planet Earth podcast, what did the first creatures to walk on land look like? I'm Richard Hollingham and I'm at the Royal Veterinary College in leafy Hertfordshire to find out about our very distant ancestors. We'll also hear about a major project to investigate the biodiversity of upland rivers. And in our audio diary from Turkey, things didn't always go as planned.
We were a bit late getting to our first sight of the day due to a bit of an accident with a hacksaw, a finger, which ended up in a visit to casualty.
One of the great pivotal events in evolution is that moment when a creature emerged from the water and, for the first time, stepped onto land. Well, it happened some 370 million years ago, but it didn't happen suddenly, nor, it seems, could the first animals actually walk. Well, with me from the Royal Veterinary College is John Hutchinson, and from the college and also the University of Cambridge, Stephanie Pearce, who've been investigating these ancient creatures known as tetrapods. So, Stephanie, what was a tetrapod?
Well, a tetrapod is an animal with 4 limbs with digits. So it's much different than what we see in a fish. Fish have fins, and all tetrapods today, including ourselves, have limbs with digits.
And what were you trying to find out then?
We were trying to find out just how the earliest tetrapods that we know of might have actually moved. We have pretty good information on their anatomy, and we use CT scans to reconstruct that in 3D for the first time. But we wanted to use that anatomy to test hypotheses or answer questions about how these animals may have moved on land when they did.
And what were the assumptions, Stephanie, about how they might have moved?
For a long time, the assumption was that they could move on all 4 limbs. So they would walk one leg at a time, just like a salamander did. But based on our research, we've discovered that these early tetrapods might not have been able to do that.
So you've got a couple of pieces of bone here. What are these?
This is the pelvis or the hip bones and the femur or the thigh bone of a big, about a 4-meter Nile crocodile, which is superficially like one of these early tetrapods. It has the same basic bones, although the proportions are a bit different.
And to give you an idea of the scale, this bone is about, well, it's not that much smaller than my forearms. This is going to be an enormous crocodile, the sort of thing you wouldn't want to come across. Yeah.
It was a pretty big animal. The early tetrapods were only a meter or 2 long, so they were smaller. But anyway, the point of having these bones here is to show that we can use, to a certain degree, the bony anatomy of an animal to figure out what kinds of motions its joints would be capable of or not capable of. And that's really what we did with these early animals, as well as some living animals, including crocodiles, to compare them with. It was we built computer models that allowed us to wiggle the bony joints around, like I'm doing here with the hip of this crocodile, move it around in a computer and see how much mobility was possible in each joint. And that would constrain what kinds of postures or movements were possible in the extinct animal.
So although you've got the bones here and you're moving this femur within the hip joint here, there's only a limited amount of movement. So from that you can tell how the legs would actually go. Even if you couldn't see a crocodile, you had no idea what a crocodile was like, you could work out how it walked.
That's part of what we tested with our study was can we actually estimate the range of motion of a crocodile's limb joints accurately. So we took the bones of a crocodile, moved them around in the computer program, and then took a real crocodile, a dead one, that was still fairly fresh, and moved its joints around to see how much mobility it had, and gradually cut away the muscles and cartilage and other stuff until we got down to just bones. And we found that actually our computer model did a pretty good job of estimating how much mobility was in each of the joints of the crocodile and other living animals as well. It seemed to work pretty well.
And then you were looking at these ancient fossils, Stephanie.
Yeah, so we applied the same procedure to our fossil animal, and when we looked at the mobility of the shoulder and the hip and the elbow and the knee, and we compared that to the modern animals that we were looking at, and we looked at modern animals in which we knew how they actually moved on land, so we could say, well, this animal has this much mobility in its hip, and we know that it uses this type of locomotion style on land. And we looked at our fossils, and we found that its limb joints actually weren't moving at all like that of living animals. And that could tell us that our fossil animal must have been doing something fundamentally different when it was moving on land.
Now, you've got an image, and you can see this on the Planet Earth Online website. You built this up from CT scans of this creature. Almost looks the head like a vicious fish, like a pike or something like that. The rib cage, yes, maybe something like an alligator or something like that. And then it's curious that whereas at the front limbs you could think, yeah, they look a little bit like legs, the back, they look more like flippers.
That's correct. The back limbs actually remind us of flippers in a seal. The lower portion of the limb is very, very flat, and there's no ankle joint, so it actually couldn't bend its foot and put its body weight on its hind legs. So these were giant flipper-like limbs that would have helped the animal while it was swimming, just like you can sort of envision for a seal.
So how would this have moved? It sort of drag itself along?
Yeah, it would have moved kind of like a mud skipper or a seal, so crutching itself along on its forelimbs, using the forelimbs together, not one at a time, left, right, but left and right, hauling itself along, dragging the tail behind it, probably to some degree dragging the hind limbs behind it. So it would have been somewhat awkward on land, certainly not a fast animal, and probably spending limited amounts of time moving around on land before going back to the water.
You're really then, Stephanie, getting a snapshot of the past and seeing how the land started to be exploited by these bony animals.
Yeah, I mean, by doing this, by making our 3D model and being able to manipulate it, we're essentially getting the first idea of actually bringing this animal back to life, looking at how it moved, and actually getting to understand the biology of these animals, how they moved, how they interacted with their surroundings, and how they made that big step from going from the water to the land.
Everything that they evolved to a certain degree was handed down to us, to frogs, to birds. It influenced all future evolution. So this is a pivotal moment in vertebrate evolution. What was going on then influenced today even. So those Olympic sprinters you might be seeing out there or have seen at the Olympics in London, what they were doing, what they were capable of, was partly determined by what these animals did and what their ecology was like, their anatomy. Some of these animals had 7 fingers and toes, or 8, but eventually they settled on 5, which is what we have. We have those same 5 fingers and toes. Why did they settle on 5 fingers and toes? Why didn't they keep 6 or 7 or 8, which they had? So there are interesting questions to be asked, very fundamental questions about the anatomy of these animals, how it functioned then, and how that influenced the way animals live today.
John Hutchinson and Stephanie Pearce, thank you both very much. You can see some images of these creatures at Planet Earth Online. You can also follow us on Facebook and Twitter, where you'll usually find some pictures of us waving microphones at scientists and unsuspecting animals. This is the Planet Earth podcast, and we've another of our audio diaries now, this time from Turkey, where a major international project is underway to investigate the North Anatolian Fault, the cause of the 1999 Izmit earthquake, which killed more than 17,000 people. Hannah Bentham from the University of Leeds joined a group of scientists installing seismometers in an area some 3 hours' drive east of Istanbul. And we join Hannah as she's driving the team to one of the sites.
We're just on our way to our first site of the day, and this site is in the most southwesterly tip of our seismic network. We've had about an hour and a quarter journey to this site, travelling along the Sakarya River. It's about 50 kilometres south, but it just takes a long time to weave through the mountains. So we've just sort of arrived to the village of the where we're going to be sighting this seismometer. We need to look for the guy who owns the field, which is the Mukhtar, the chief of the village. So we just need to get in touch with him, and then we can hopefully get this instrument installed. So we've just parked up on the edge of the Mukhtar's land, and though this sort of area where we have this either dried up lake or meandering river basin is really quite flat, there's a couple of mounds, so we're just clambering our way up these. And what's around me, there's a lot of trees. It's a very green area, completely surrounded by mountains. It's quite phenomenal, and we've got a field of corn and all these different types of flowers, poppies, and these yellow flowers. I'm not really sure what those are. But there seems to be some discussion as to or where we're going to put this seismometer. I'm going to go and have a listen.
Ben de oraya kadar git. Beni kim götürecek eve? Ben size götüreyim ya şeye yıkacak.
The point of this project is to understand more about the processes of the fault and the earthquakes that occur on this fault. We can do this by installing 63 new seismometers in the Sakarya province, and these seismometers will be used to detect earthquakes from all around the world. And as these earthquakes go off, the energy ripples through the earth. It changes depending on the material it travels through. And so we can learn more about the ground and the fault beneath the stations by looking at these ripples as they occur at the stations. I have never experienced an earthquake before, but luckily I was able to speak to Ismail in a cafe, and he was present in the Sakarya province during the 1999 Izmit earthquake.
Yeah, I remember it quite well. It was the first biggest earthquake that I have experienced in my life. I just felt the earth moving under my legs, and first I heard a big explosion. I thought that a big bomb exploded somewhere around me. I felt real terrified. I just made sure that my children and my family took out safely. We were lucky that we were living in a one-story house. So when I went out, I tried to call my friends and some family relatives, but I couldn't get in touch with them because the telephone lines weren't working, and it was a big shock for me. I can't put it in words. It was really like a doomsday.
Just to introduce Dr. David Cornwell from the University of Leeds. And David, what are you doing here?
Well, I'm digging a hole about 1/2 metre deep. We're going to put the seismometer down at the bottom of the hole. We'll put some sand down first, level the bottom of the hole, and put a plate on top of it, normal floor tile, and then the seismometer will rest on top of that, and then we will backfill it with the earth.
We were a bit late getting to our first site of the day due to a bit of an accident with a hacksaw, a finger, which ended up in a visit to casualty. So we arrived a bit late and about midday, so we're in a really, really remote village in the middle of the mountains, and we are struggling to find somewhere for food. And so we spoke to some local farmers asking them where we could eat, and they brought us some bread, some spring onions and some strawberries. And so we thought that was it, and then they've invited us in for lunch. So I've stuck out to do a bit of a recording. I just wanted to express how amazing the hospitality is here. We are installing an instrument in this man's land, and they invite us in for lunch and bring out tea, biscuits, loads and loads of tomatoes, apples, cucumbers, the brightest tomatoes you've ever seen. And it's just amazing how warm these people are. I'm really, really touched today. Once the seismometer is in the ground and recording, one of the things we have to do is a stomp test. And what that consists of is 3 very large stomps on the ground, followed by a 1 large stomp. And what we have to do is to check that we see these stomps in the waveforms on the computer. So as you can hear in the background, stomps are going on. And just looking at the computer, we see the 3 components, the up, so the Z component, the north and the easterly components, and we can see that the stomp tests are coming in now. Yes, we see 1, 2, 3 wiggles, and then followed by 1. Brilliant. So the seismometer is working well. We're just packing up the car and going to leave the site, and therefore we're done for the whole day. Currently we've deployed 62 of the instruments, so another 4 need to be done tomorrow. And say it's been a really good day. We met some fantastic people, seen some beautiful sights, and done some good science.
Wonderfully evocative. Hannah Bentham's audio diary from Turkey. You can hear all our past audio diaries at Planet Earth Online. I've also asked Hannah to send us some pictures which we'll put on our Facebook page. What's the value of a river? And how do you balance the services it gives us, such as clean drinking water or drainage, with its biodiversity? Isabel Durrance from Cardiff University is leading the Duress project, which is examining the role of biodiversity in providing these ecosystem services. I met Isabel and her colleague Steve Ormerod beside a stream on the outskirts of Cardiff.
Rivers provide many services that include, for example, fish for fisheries and anglers, quality water, riverbirds that we appreciate for their cultural value. All these services that rivers provide can only be provided when the river functions properly.
So what are you looking to do then with this project?
Well, the main point of this project is to try and understand the role of biodiversity in providing these services. When we do our experiments in the lab, it looks like the river organisms, the way they function together, the way they modify their environment, is what provides these services that we depend on. What we think is that if we do manage our catchments to help those river organisms, then we would be able to sustainably use these ecosystem services that the rivers provide.
Are you putting a value then, Isabel, on the various plants, the animals, the microorganisms in, a river such as this?
It's not just about putting a value, it's trying to understand the role of biodiversity. So what we want to do is establish the link between biodiversity and ecosystem services. And then, of course, those ecosystem services, we need to find what their relative value is. Is it more important for you to have fish in the river, or is it more important for you to have fresh water, quality water, or is it more important for you that the price of maize is low?
So is this all about us, Steve? Because that's the danger of this, isn't it? When we talk about ecosystem services, it's what's in it for us.
So this is, at the heart of the ecosystem services paradigm, essentially. And on the one hand are some conservationists who like to believe that we protect ecosystems because they have all kinds of aesthetic values and it's our ethical duty to protect them. And on the other hand is this utilitarian notion that we essentially are ascribing a value for our own exploitative purposes to ecosystems. My own view, in fact, is that these two approaches exist absolutely side by side. Ecologists, environmental scientists must demonstrate the human value from ecosystems, but at the same time we have all kinds of legislation that protect conservation value. The ecosystem services idea isn't replacing the nature conservation instruments we have at our disposal already.
So in putting a value on the biodiversity of, say, this stream in front of us, with its insects, its fish, and the plants that are in a canopy over it, does that make a difference to the way nature is protected?
So there are some people who believe that if we don't put a value on nature, then the default value will be zero. And in a world where essentially the need to exploit resources, we are now past our 7th billion person on Earth. We're moving towards 8 or possibly 9 or 10 billion. Unless we do protect the resources that we need for the way that they sustain us, then a lot of our future is at risk. And in terms of adding to the political weight of debate, valuing our ecosystems appropriately has become absolutely critically important.
Steve Ormerod and Isabel Durrance from Cardiff University talking about the Duress project. And that's the Planet Earth podcast from the Natural Environment Research Council. I'm Richard Hollingham from the Royal Veterinary College here in Hertfordshire. Thanks for listening.